So today I want to talk about more general concentration. So last time we talked about concentration for Gaussian random vectors, but we looked essentially on functions which were linear functions which were sums of independent random variables. Okay, but in general we have more general functions, and that's what I want to cover today and probably also next time. So it's again about concentration. And we will do it again for the Gaussian random vectors, because that's maybe the most important ones, in particular the ones which we can treat mathematically very nicely. So for Gaussian random vectors, but the functions we consider of them are now in general non-linear. So not just sums of things, but of course we need some condition, and it will be Lipschitz functions. So the condition we need is that we have Lipschitz functions. Yeah, so I will explain what we mean exactly with this. Okay, so recall what we did up to now. So we considered concentration of linear sums. So that was maybe last time. So we consider a function of our vector, and our vector has components t1 up to tp in p dimensions, and what we considered was a sum of functions of the components. So it was something like f1 of t1 plus and so on fp of tp, and last time in particular we looked on the case where those functions here are t squared minus 1, and all of them are the same. Okay, and then we could develop a nice machinery which works also more general than just for Gaussian random vectors, but there we could do it very explicitly. So we have a general machinery for getting concentration estimates. Good, but now, I mean, this is a very special situation, and maybe we also would like to have to understand or see concentration for more nonlinear stuff or general stuff. So now we consider functions, okay, which in general are non-linear, which are not of this form. And so, I mean, we have functions. Okay, I mean, at the moment I'm not really writing down anything. I'm saying it's just functions where we don't make this linear assumption, but of course we need some assumption. I mean, we don't have concentration for arbitrary functions, so we need something for those functions, and maybe the idea is maybe phrased in this phrase by Michel Talagrand by saying that a random variable that depends in a smooth way on the influence of many independent variables, but not too much on any of them, this is essentially constant. Essentially constant means we have concentration. For most instances it's close to this constant. But what we need is a function that depends in a smooth way on the influence on many independent variables, but none of the variables should have a dominating influence. Okay, so this is, okay, maybe I'm not writing it down, but so this is a phrase of Michel Talagrand, who did a lot in this context. But all this concentration theory, I mean, there are a couple of names, Ledoux and so associated to this. And maybe just to give an example, of course, so what, for example, works, where we have a function which depends on many variables, but no one is dominant, is things which we considered up to now. For example, if we take the average of t1 squared plus tp squared. So this is something of this form. But if we compare this with a function of p variables, where we only take the square of the first variable, then it is clear that here we expect concentration, and essentially we saw it last time. But here, of course, I mean, we don't have concentration. I mean, most of the variables don't play a role. This is a one-dimensional problem. T1 squared always has the same distribution, which is smeared out, which is not concentrating if we make the p bigger, because the other variables don't play a role. So this function is not seeing the other variables. So it depends on a smooth way on one variable, but this variable has dominant influence. All the others don't play a role. I mean, here all the variables have some kind of the same influence. Okay, so that's the idea. So in both cases here, I mean, the expectation is 1 if we take for the g's, if we take here our Gaussian random variable. So the expectation of f is 1 as well as the expectation of g. But still, they behave in a very different way. Okay, so f concentrates about its expectations. F concentrates about 1 for large p, but g has always the same distribution which is spread out and which does not concentrate for p. I mean, it doesn't really depend on p. So g has independent of p always the same spread out distribution. Okay, it's good. So we have to make a bit precise what do we mean with that we have a function which depends in a smooth way on all variables without having one variable which is, or several variables which are dominant, and the right setting for this are Lipschitz functions. So that's the one which we will consider and for which one can prove concentration. Okay, so let me define and talk a little bit about what is a Lipschitz function. So this is something which probably you should have seen before. So function f. So let us consider our setting. We go from Rp to R. So we have a function of our p-dimensional data set. So we call this is Lipschitz, and Lipschitz has a constant in it. So maybe if we are more precise, we call it L Lipschitz, and L is the corresponding constant. So this is L Lipschitz. So Lipschitz was a mathematician, and this L is now a number. Okay, this L it's a Lipschitz constant, but it's a number which will appear in the definition, and we call this number then the Lipschitz constant of the considered function. So this is a real number bigger than 0. Yeah, so what is the definition? I mean, if we can control the distance after applying our function compared to the distance before. So I mean, f should not increase distances too much, at most by this factor L. Also, if I compare f of x minus f of y, this should be less or equal L times the distance between x and y. So it's a kind of, I mean, it's a stronger version of continuity. It's really saying us that we can control what happens if I change the argument. I can control this in a linear way. And not just in the neighborhood of a point, but this should be true always. So even if for points which are far away. Okay, so this should be true for all. I mean, our functions, let's say, are always defined everywhere. Of course, if they are not defined everywhere, then we just require this on its domain. Good, okay, and this L is the Lipschitz constant. And I mean, L equal to 1 maybe is an important case. So maybe if I say Lipschitz, okay, I might mean Lipschitz with any constant, or maybe specifically with constant 1. But okay, maybe it's better to really be precise. When I mean constant 1, then it's 1 Lipschitz. Good, okay. But maybe right away, of course, we should think a little bit about what happens, maybe if we're composing Lipschitz functions and things like this. Because in general, I mean, of course, if I have a neural net, I start with my data set R to the P. Maybe at the end I'm going to R, but in between I have other mappings where I also are in high dimensions. So maybe we should also have this notion where I'm not going from Rp down to R, but to some other dimension. And of course the definition is the same. So I mean, whenever you have a mapping between two spaces where you have a distance, you can define this. But so maybe let me also just write it down so that we can discuss things a bit more general. as a mapping between arbitrary spaces. Also, more generally, I mean, I could have written it down directly there, but let me do it this way. So if I have a function which goes from p dimensions to m dimensions, then I also say this is L Lipschitz. If I have the same, that the distance between f of x and f of y, and of course the distance now, I mean, this is the norm in R to the m, the Euclidean norm. I mean, we could take any norm, but we usually take the Euclidean norm. If this can be controlled by L times the distance between x and y for any x and y in R to the m. Okay, so that's the set of functions which are very nice, and I mean, it's important that in the context, for example, of neural nets, the operations which we are doing are of this form. Okay, so this is really a set of functions which are relevant in our setting. And maybe first one should note that, of course, I mean, a function which is Lipschitz, this is in particular continuous, because if x or if y goes to x, then of course this tells me that f of y goes to f of x. So it's continuous. It's not necessarily differentiable, but if it is differentiable, then essentially this here, I mean, this here is a condition on the difference quotient. So this means that the derivative should be bounded by L. So Lipschitz function which is differentiable, then essentially this condition here is telling me that the derivative is bounded by L. And in high dimensions, the derivative is a vector, or the vector of the partial derivatives, the gradient, that this has a norm which is bounded by L. So essentially, I mean, it's a kind of condition on the derivative. I mean that the function is not varying too much, but a condition which can also be formulated if my function is not differentiable. But of course, many functions are differentiable, or they are at many places differentiable at least. But so let me write this down as a remark. So a smooth or differentiable function f, I mean, this is Lipschitz if and only if its derivative is bounded by L. So this is the Lipschitz. A differentiable function f is Lipschitz if and only if its gradient vector okay, so let me talk about the function going from r to the p to r, because then I mean the derivative is just a gradient vector. So let's say here from rp to r, and then I have the gradient of my function f at a point is just a vector of partial derivatives. I have p coordinates, so I have p partial derivatives, and the gradient is the collection, is the vector of all those partial derivatives. So it's d of f derivatives with respect to the first coordinate and so on up to df of x with the last coordinate. So this is a vector for each x. It's the vector of the partial derivatives, and this is a vector in r to the p, and so I mean the norm of this vector is bounded, and it's actually bounded by this number L. So this is bounded. So Lipschitz for continuous, for differentiable functions is saying that I have a bound on the derivative. And bound on the derivative has this idea that the function is not varying too much. I can control the variation of the function. And that's also what Lipschitz is saying more generally. Good. And of course, there are functions, interesting functions, which are Lipschitz but not differentiable. And maybe the ReLU function is a prototypical example of this. Maybe because this, I mean, those are the nonlinearities which are applied component-wise in my neural nets. They are typically things which are not differentiable, at least not differentiable everywhere, but which are still Lipschitz. So they also fall in this class. Second part here. So let's say interesting. Interesting, of course, is not very precise, but at least in the context of our neural networks, we quite often have to deal with non-differentiable functions, but they are still, usually they are Lipschitz. So interesting non-differentiable Lipschitz functions are, and now, okay, now ReLU is of course a function from R to R. So this is the case when p is equal to 1. So Lipschitz functions are, let's say, for p equal to 1, the ReLU function, rectified linear unit, which is, which is nothing else than this function which is 0 up to 0, and then it's just a linear function x. So f of t is either 0 on the negative side, and it's equal to t on the positive side. Okay, and of course this is Lipschitz, and what is its Lipschitz constant? What should it be? Yeah, according to what I said before, if it is where it is differentiable, okay, I should take the derivative. Okay, so here it would be 1, here 0, and of course here, okay, one has to check about the point 0, but there's still, of course, you have this estimate with L equal to 1. Okay, so this is 1 Lipschitz. So the constant is equal to 1. Good. Yeah, okay, so this are some generalities, but then maybe another one is that usually I'm building my neural net out of compositions of functions. And so the one of important point is that the component-wise, or the composition, is also, Lipschitz is preserved. Okay, maybe I should be more precise. I'm doing compositions of functions. I go from one layer to the next, but sometimes I also do component-wise applying these non-linearities. And both those operations preserve the Lipschitz stuff. So maybe let me first address this component-wise application, because component-wise I apply, for example, the ReLU function. So component-wise I apply a Lipschitz function, and then I'm saying that also then the whole function together is also Lipschitz. And of course, we have to see what happens with the constant. Of course, somehow we have the feeling, okay, if I do operations with Lipschitz functions, the Lipschitz property should be somehow preserved, but the constant, of course, could become worse and worse. And of course, if the becoming worse would depend on the dimension, then this would probably be quite bad. So it's the question: what happens with the constant? In particular, if I have high dimensions, does the dimension show up in this? Okay, so let us first look on the component-wise application of Lipschitz functions. And I'm claiming this is again Lipschitz. Okay, so maybe this you believe, but the question is what happens with the constants. Okay, so let us be more precise. So assume I have, okay, I'm in R to the P, so I have P components, and now I do something component-wise, and on them I apply functions like this. So I apply, let's say, functions, let me call them F1 up to Fp, but each could be, for example, the ReLU function. Those are functions from R to R, and I assume they are Lipschitz with some constant L. And now I lift those guys to mappings in the p-dimensional space. So now I build from this a mapping which goes from Rp, and now I'm staying in Rp. So I'm essentially here in this more general situation where I'm going from Rp to Rp And here I just apply on each of my components just one of those functions. Okay, so I do this here, where f of t1 up to tp is just, applying on the first component, I apply f1. On the second component, I apply f2, and so on, up to the last component, where I apply fp. So I'm mapping p-dimensional vector into a p-dimensional vector. And then I'm saying that this is again Lipschitz, and it's just the same constant here. So I'm assuming all of them have the same constant. Of course, I could have different constants, but then I should take the maximum of them, which would show up here. Okay, so I assume each of them has Lipschitz constant L, and I'm saying this is not getting worse if I do it here in this dimension. So I'm saying this is also Lipschitz. Maybe this is not so surprising, but I say I have the same L. L is somehow the sensitivity of my function to variations in the arguments. And that's what I want to control. My function should not depend too much on variations in the arguments. Okay, so let us check this. This is, all those things are very simple. One just has to write it down. But it's important to have those statements and get a feeling, or really see how compositions or component-wise applications, how they are related with the sensitivity of my function. Yeah, so let me write this down. So what I have to check is what is the distance of f of x and f of y after applying this. So I should compare f of x with f of y. And I have the Euclidean norm, which is the square root of the sum of the squares. And the square root is always a bit annoying. So it's always better to look on the square of this and do the calculations for those, and at the end take the square root. Okay, and so what is this guy here? This now, of course, is my p-dimensional vector, where at each component I apply the component k, I apply the function fk. So there I have just the corresponding difference of those component functions applied to the corresponding components. And the components of x I'm calling t1 up to tp, and the components of y I'm calling s1 up to sp. So this here is then f1 of t1 minus f1 of s1 up to fp of tp minus fp of sp. Just taking the corresponding function on those components. So this here is the vector, and of this vector I have to take the norm squared. Okay, and so this means, of course, I have to take the sum of the squares of the components. So this is, the first component is f1 of t1 minus f1 of s1 squared plus and so on. The last component is fp of tp minus fp of sp squared. Okay, and now for each of them, of course, I can apply the Lipschitz condition for the corresponding f. So f1 is assumed to be Lipschitz with constant 1. So I can estimate this here against the norm. Okay, now I'm back in R, so the norm is just the absolute value, t1 minus s1 times L. And because I have the square here, I have to square here everything. And the same here. Here I use the Lipschitz condition on the function fp with the same constant L. So I get here L squared tp minus sp squared. Yeah, okay, and now you see I can estimate this against, the L squared is the same for all of them. So I can take this out, and I have here L squared, and then I'm remaining here with the sum of t1 minus s1 squared plus and so on tp minus sp squared. Yeah, okay, but of course, the sum of the squares of those guys is just the square of the norm of the vector x minus y, because x minus y has the components t1 minus s1 and so on up to tp minus sp. So this here is the norm of x minus y squared. So what we get from this calculation, so if I now take the square root, so you see here coming back to L, I have that f of x minus f of y, the norm in R to the p is less than L times the norm x minus y. Okay, so you see, I mean, this component-wise application of Lipschitz functions is again a Lipschitz function, and the L is the same. In particular, it doesn't matter to which, what is the size of the vector to which I apply it. The p is not showing up here, which is good, because otherwise it wouldn't be so interesting. Good. Okay, and then maybe the other thing is that if I have compositions, of things, that's here. This component-wise is maybe what I'm doing in each layer, where I apply component-wise something. But then, of course, I have mappings between my layers, which usually are linear mappings, and linear mappings are also Lipschitz, because they are differentiable, and okay, they are bounded by their norm. So okay, so between the layers, I can say I have Lipschitz functions, and then I do this component-wise stuff, and then I compose all these things together. So it's also good to see whether compositions also preserve, or how they preserve the Lipschitz condition. Okay, so let us also look on this. Yeah, so I'm saying the composition of Lipschitz functions is also Lipschitz. Compositions of Lipschitz functions is Lipschitz. And let me look at example, maybe just to be a bit more precise. I have a function where I'm going from Rp to Rp, and this, for example, could be a component-wise application of Lipschitz functions. Okay, and then I have another functions which goes from Rp to R. And in principle, I could have all dimensions here, but okay, maybe this is just to maybe have a bit more contact to our neural nets. That's things which happening, for example, in a neural net. So I go from Rp to Rp, where, for example, I do the component-wise application of Lipschitz functions, or maybe I also just do a linear mapping, and then at the end I'm going down to R. And let us assume that this here is L1 Lipschitz, and the second one is L2 Lipschitz. Okay, and then what is now the composition? So the composition H, which is G after F. So this goes then from Rp to R. So first I apply F, so I go from Rp to Rp, and then I apply G and go down to R. So here, of course, X goes over HF, and this composition, of course, means I take G of F of X. Or maybe as a diagram, I go from Rp to Rp with my F, and then I go from Rp to R with my G, and the composition does this in one step directly. So the H is the composition G after F. Yeah, first apply F and then G. Yeah, it's an unfortunate convention that, okay, the diagrams, it's written in this form, and because we are writing from left to right, it looks here the other way around. You always have to remember that this means you apply F first and then G. Okay, anyhow, but we all know this. Okay, so I'm claiming that this is also Lipschitz. of course, because it's an iteration of the Lipschitz condition twice. I mean, this is clear essentially, but let me write it down so that we also see exactly what happens with the constant. So I have to check the Lipschitz condition for h. If I compare two arguments x and y, but of course h is just g of f of the argument, so here x, and here it's g of f of the argument, so here it is y. Yeah, and now of course I have here, I use now the Lipschitz condition for the function g for the argument f of x and the argument f of y. So this can be estimated against the Lipschitz constant for g, which I called L2, times the distance between the arguments. But the arguments of g is here f of x, and here it is f of y. Yeah, okay. And here, of course, I'm now in the RP, so this is the norm in RP. And now, of course, I still have to estimate this further, but now I can apply the Lipschitz condition for f. So this here can be estimated against the Lipschitz constant for f, which I called L1, and then times the distance of the arguments, which is now x minus y. Okay, and that's, of course, exactly what I need for seeing the Lipschitz condition for h, that I can estimate it against the difference of the arguments, and then I have a constant, and of course you see the constant which I have here is now L1 times L2, x minus y. Okay, so there is now a combination of the arguments which shows up. I mean, composition is like multiplication. If I have linear maps, it's indeed matrix multiplication, so it should be clear that I should get here a product of the constants. But so this shows that h is indeed Lipschitz, and the constant which I need for it is the product of the constants for the two functions which I composed. Okay, yeah. I mean, now that the constants are changing, this might look bad, but actually, I mean, for example, if I have one Lipschitz function, so if the L's are 1, then of course the product doesn't make it worse. Of course, if I have big L's for each of them, and I multiply them, then it's getting worse and worse. Okay, so I mean, I really should be careful that my Lipschitz constants for each of the steps I'm doing is, let's say, less than 1. Because then multiplying is not making it worse. If it is strictly less than 1, it even makes it better. Okay, but I mean, if I have one Lipschitz functions, then also the composition is a one Lipschitz function. Okay, so in particular, if L at 1 and L2 are both equal to 1, then the product L1 times L2 is also equal to 1. So this means the composition of one Lipschitz functions is again a one Lipschitz function. Okay, and that's good. So then we can control things. But it means that we should be careful what the constants are. Good, so now, yeah, we have kind of idea about Lipschitz functions. So any questions on this before we look now on concentration? So what we really want to see is that for such functions we have concentration. That's our main goal, and this is indeed true, of course, otherwise we wouldn't be talking so much about this. And so let me formulate the theorem. And again, I mean, this is true in more generality, but we do it for our Gaussian random vectors, because there are very nice proofs which are on a level so that we can do it. Otherwise, we would, for more general statements, okay, the proofs are getting more complicated and technical, but maybe they are not adding so much for us. Also, I just want to show the nicest situation where we can use nice properties of Gaussian distributions for getting a very nice proof. But still, it's not trivial. I mean, it's still a bit involved. We have to work, and of course, it should be more involved than what we did last time for the specific class of functions which are sums, and already this was not so easy. But somehow we are following same kind of idea. Okay, but let me first write down the statement and then go step for step through the proof. Yeah, so here's the theorem. So this is the Gaussian concentration for Lipschitz functions. Gaussian concentration for Lipschitz functions. Yeah. So what is our setting? We consider a function f from p dimensions to R, and we assume that this is a Lipschitz function with constant L. So let this be an L Lipschitz function. Okay, and then we want to apply this to vectors in R to the P, but those vectors we take them as Gaussian random vectors, so we have our Gaussian probability measure on them. And with respect to this measure, we want to measure what are somehow deviations of this function from the expected value. So then we have, and again we take a standard Gaussian random vector. So we take a standard Gaussian random vector X. Standard Gaussian means its distribution is the normal distribution in p dimensions with mean 0 and covariance matrix identity, which means nothing else that all the components of this vector are independent, and each of them has a standard Gaussian distribution with mean 0 and variance 1. Okay, and of course in high dimensions, usually if you take a function of this will get quite big, and usually, I mean, then you maybe also normalize your function so that you get something independent of p, for example, for the expectation or so. But here we are not doing this here. So here, I mean, we don't do normalization here because the normalization would depend on the function which we consider, and we don't want to be specific for this. So we formulate it in this way, and so we say for such a Gaussian random vector, we have a concentration estimate. Concentration estimate, and this is an estimate for the deviation from the expected value, and the deviation should be given by alpha. So for any alpha bigger than 0, we have that the probability of the vectors in R to the P, probability measured with respect to our Gaussian distribution, for which the distance, the deviation of f of x from the expected value, I mean, that's the idea. I mean, my function should be close to a constant value, and this constant value should probably be the expectation over all values. So we compare usually with the expected value, so the expectation of f of x, the deviation of any f of x from this, that this is bigger than alpha. This can be estimated by 2 times the exponential of minus alpha squared divided by 2L squared. So here the alpha shows up in this quadratic way. That was also the nature of our concentration inequalities. We have an exponential decay in this guy here, and usually it's in the square, and then the Lipschitz constant also shows up here. I mean, if I have here a big Lipschitz constant, then of course the decay will be smaller. Okay, so if I have 1 Lipschitz functions, then this is equal to 1, but it's good to have a control on this. Good, okay, so that's what we want to prove. That's a general statement. And I mean, you have statements of this also for situations where your random vector has independent components, but they might have other distributions. But then things are getting more complicated, and you need some additional assumptions or so on. Okay, and we are doing a proof of this, which will rely quite a bit on the fact that we have Gaussian distribution. We will see this later, why we can deal with this very nicely. But let us start with some general considerations, which essentially are simplifications of what we can assume in our proof. So let us start with the maybe more trivial things, general things, so some simplifications. Okay, so first of all, we have here the expected value, but of course we can shift our function by instead of looking on the function f, we can subtract its constant value, the expectation, and then we are shifting our function from a function which has some finite value of the expectation to a function which has expected value 0. And the Lipschitz constant does not change under this. Okay, so I mean, if I get my estimate for the function after the shift, then I also have it for the one before the shift. And after the shift, I mean, then this guy here disappears. Okay, so shifting. So I'm shifting my function f, or I'm replacing f by the function where I take f of, maybe here's argument, here's also the argument, and then I'm subtracting just the constant, which is just the expected value of my function. Then and I call this, let's say, g, and then I'm doing g for this way, and the only observation is the Lipschitz constant does not change if I'm doing this shift. So the Lipschitz property is not affected. So we can actually assume in our what we have to prove that the expected value is equal to 0. Because then by shifting it back, we get it also in a more general, in the case where it's not 0. So we can assume that the expected value of f of x is equal to 0. Okay, and thus, so we only have to prove, and then of course in this case we have to prove the same statement, but the expected value is now gone. So we have to prove the probability of the x's for which f of x is bigger than alpha is less than 2 times the exponential minus alpha squared by 2l squared. Okay, and now maybe we can think about why do we have this factor 2 here? So where does this come from? This is just on general grounds. It doesn't have to do with any Lipschitz condition or so. I mean, it's the fact that we have here actually a condition which involves the absolute value. And the condition on the absolute value are actually usually 2 conditions. And so this here, this here is the probability. Either this f of x is positive and then it has to be bigger than alpha, or it is negative and then it has to be less than minus alpha. So if I say the absolute value is bigger than something, this means the quantity itself is bigger than this something, or it is less than the negative of this something. So this means this p here, this condition here is either, okay, maybe I'm not saying it for the probabilities because my functions are not symmetric, so I cannot really say that the probabilities of both are the same, but at least I can say that this event here, this condition here, that this is bigger than alpha, this is either that f of x is bigger than alpha, or that f of x is less than minus alpha. Okay, and this here, of course, I can also say that instead of having the minus here, I bring it on the other side, that minus x minus f of x, and then the inequality gets reversed, is bigger than alpha. And then you see what I have here is that I say I have a function, my Lipschitz function should be bigger than alpha, or minus of my function should be bigger than alpha. But if f is a Lipschitz function, minus f is also a Lipschitz function with the same constant. So this means if I estimate this event here by something like this, then I mean for this event I have the same estimate. And then the probability of this here is less than the probability of this plus the probability of this, but if then I have the exponential estimate for each of them. So this means what I really have to show is I can estimate this without the absolute value against this exponential term. And then for the absolute value, I get just this factor 2. That was as before in the case of the linear situation. So I mean the probability of this event, which is the union of two events, is of course less than the sum of the probabilities of this plus this. And then if I can estimate each of them by this, then I have this factor 2. But of course I just have to do this estimate once, because if I have it for f, then I have the same estimate for minus f. Because minus f satisfies the same assumptions, the Lipschitz assumptions, than f does. Yeah, so what we really have to prove is the one-sided estimate in this exponential, with respect to this exponential decay. Under our assumptions as we have it here. So I have to prove the probability of the vectors, of our Gaussian random vectors, for which f of x is bigger than alpha. This can be estimated by e to the minus alpha squared divided by 2l squared. And of course under the assumption that the expected value is equal to 0. Okay, yeah, maybe under the assumption that the expected value of f of x is equal to 0. Good. Okay, and then we go, a little bit on, make simpler, further simplifications, that actually we can also assume that we have a smooth function, a differentiable function, because then the Lipschitz condition is actually conditioned on the derivative, and this will be easier to use later. Okay, and for this one has to think that you can approximate general Lipschitz functions by smooth Lipschitz functions, and then the statement goes also over to this. Okay, so this is something technical, which is maybe not totally clear, but this can be done, and so we assume this. So we will only prove the statement if our Lipschitz function is differentiable, and then the Lipschitz condition is actually telling us that the gradient of the function is bounded by L. That's how we are using the Lipschitz condition. Okay, so since one can approximate arbitrary or general Lipschitz functions by smooth functions, Lipschitz functions, and then so this means we can restrict the case where the f which we consider is smooth. So I mean, this means differentiable, and then the Lipschitz condition can be expressed as a condition on a derivative. So this means we really have a function where we can control the derivative, in the form that the gradient, so the vector of the partial derivatives at any point is less than L for all x in R to the P. Okay, so that's how we use the Lipschitz condition in this setting. Okay, and what we are going to prove is actually, okay, we are not getting this factor here, but we will have some constant here. So we will have a 2 over pi squared there. This relies on the proof we are giving. So we are not getting the optimal constant. So one can prove it with in this form, but this requires more work, more other tools. And the tools we are using will give us a little bit worse constant here. But usually the constant are not, just having constants in these exponential decays are usually not a problem. So if you get a little bit worse, this doesn't change much. But just to say this, so instead of, so what we really want, or what really is true, so namely that we have this exponential minus alpha squared divided by 2L squared, we will get the exponential of, and so here we have minus 2 divided by pi squared, alpha squared divided by L squared, or maybe an additional L squared. Okay, whatever. So we will get a different constant here, but okay. This is the artifact of our proof, but on the other hand, our proof is quite elegant and nice, so okay, I think we are happy to pay this price. Okay, so I would say, what the advantage we have an elegant proof, and maybe this proof goes back to Morey and Pizier. Okay, and maybe the statement in this form also goes back to them, but similar statements have been around for a while, also by other people. Okay, good. But so now we have made some simplifications, but now I think we really should get started with the proof. We really should do substantial work. I mean, this here was just saying that, okay, we can make some simplifications, assume more properties on our functions. Okay, but now let's get started. And we start in the same way as we did it last time, namely by going over from the estimate which we want to estimate where we take essentially the exponential of what we want. So we go again over to the generating moment series. So for each, and we put in a lambda there, which we choose later to have some freedom, some flexibility. So for each lambda, and the lambda will be determined later. This will, of course, depend on our setting. So be determined later. We leave this open, but I mean, all statements which we have are true for any lambda. So what we want to estimate is the probability that my function is bigger than alpha. Okay, but we go over to essentially moments of my variable. F of x is the variable which I want to understand. I go over to moments, and I want to consider all moments together, and I'm doing this in a nice way by taking the exponential generating function. So I say this is the same as if I just exponentiate this inequality. So I take here e to the lambda f of x, and then this has to be bigger than the corresponding exponential of this side. So it has to be bigger than e to the lambda alpha. So this function e to the lambda something, this is a monotone function. So it doesn't reverse this sign here. Okay. And of course lambda has to be positive, because otherwise it would be decreasing, and then of course it would reverse. So it's important here that lambda is positive. So we have this here, and now this here we just estimate by Markov. I mean, e to something is a positive function, and Markov inequality gives us an estimate for probabilities of positive functions. So by Markov, we can estimate this, and what do we have to take? We have to take the expected value of what we have here. So we take the expected value of e to the lambda f of x, and then divide it by what we have here, by what we compare it. So we have to divide it by e to the lambda alpha. Okay, and now we are, now we are at the same point where we were when we did the special situation where the f was the sum of independent guys. But then, of course, we could here continue very nicely because, e to the sum is the product of e to each term, and because the guys are independent, also the expectation factorizes. So essentially, we could bring back understanding this to understanding the corresponding quantity, where we only have here one of the variables involved. But now, of course, we cannot do this. This f is now not a sum of independent things, so we cannot continue as we did last time, but somehow we still, we still need something that we can estimate this here by, hopefully something which is of the form e to the lambda squared, because that was what we wanted. Okay, so we have now to work with this in a we need different tools for dealing with this. Okay, and we need, in particular, a general ingredient, which is a general inequality for integrals. If I apply convex functions to integrals, or take integrals of convex function applied to what I'm integrating over, and there's a very general, very important inequality. So maybe probably you have seen this or no? Any idea what I mean? Exactly, Jensen. Okay. So I recall this and talk about this, and because it's so important, I will even give the proof, because it's also quite simple somehow. But it's good to see this. Okay, because this will be what we are going to use here. And of course, we are using this because this exponential function is convex. Okay. So you see, we have here expectation of a convex function. So that's really a context where Jensen makes its appearance and is important. Okay, so I stopped the general proof now. I make a short break here, so we will of course continue the proof later, but let me first recall Jensen inequality, and then we will use it in this context. So what is the statement of Jensen's inequality? So let me formulate it in our setting. So we have a random vector in R to the P, where we have a probability distribution. Let's say I have a probability, let's say density psi, with which I integrate. So this means for any function which I apply to my vector function in R, we have the expected value. It's just recalling notation. So if I take the expected value of f of x, this is the integral of f of x integrated with respect to the density and the dx, the usual integral. Okay, and now what we want to do is we want now to apply a convex function, we want to compare if I take a convex function of this guy or if I take a convex function of the result. And Jensen allows to compare this for convex functions. So convexity is, of course, crucial here. So I consider now a function h. This is a function from R to R. So this should be convex. Okay, everybody knows what convex is, but I will recall in a minute what it means. And then the statement is, then we have, exactly like here, for any and we have for any f from Rp to R, and any means here of course measurable and integrable, so that the integrals are finite. But then I have that if I apply my function to the result of the integration, which here is the expectation, so I take the expected value of f of x, that this can be compared to the situation where I apply my convex function directly to f of x and then integrate. So it's about to exchange, applying the convex function and doing the integration. And I can compare this against each other. So it is less than the expectation of h applied to f of x. Good, okay. And in particular, I mean, I can take for my convex function these exponential functions. So maybe let me also write it down here, because that's maybe the situation where we are using it. So in particular, since for any lambda, so the function h of t is exponential of lambda times t. This is convex. And I mean here it's, okay, it can be lambda positive or lambda negative. I think, I mean, it's always, it goes like this, or it goes like this. It's, it's convex for all lambdas. Huh? But of course the lambda which we have might be restricted later, but this is for any lambda. So for any lambda, fixed lambda, this function is convex. So I can write this here for this exponential function. So we have for any lambda in R that the exponent of lambda, taking this function of the expected value, so this is the exponent of lambda times this value, expected value of f of x, that this can be estimated against taking the expected value of applying this exponential function to f of x. So it's less than the expected value of e to the lambda f of x. Okay, okay. So something like this we will use later, but maybe let me first talk a little bit about convexity and Jensen's inequality in general, and also give you a proof of Jensen. So maybe first let me recall what is a convex function. So the fact that h is convex means, of course, by definition, that if I take h of a convex combination of 2 points, it is less than the convex combination of the function of those points. So if I take h of alpha 1 t1 plus alpha 2 t2, then this is less than alpha 1 times h of t1 plus alpha 2 h of t2. Where t1 and t2 are arbitrary elements, and alpha 1 and alpha 2 are positive coefficients which sum up to 1. So I mean, here alpha 1, alpha 2 bigger than 0, such that alpha 1 plus alpha 2 is equal to 1. Of course, I could say I have here alpha and I have here 1 minus alpha. But in this form, maybe it's better if I want to extend this to more. Okay, and of course, I mean, this means, of course, that a convex function always lies between the line segment which connects 2 of the points on this curve. So if I have here my convex function, and I take a t1 and a t2, t1 and t2, I'm comparing my function with the line which goes through the 2 points at to the 2 points on the graph of my convex function. And of course on this side I'm taking now a convex combination of these 2 points, which is something here in the middle. And then h on this side is this guy here, and on the other side I'm just taking the convex combination, the corresponding convex combination of what I have here and what I have here, and this is of course the corresponding point on this line segment. So I'm always saying that the curve between T1 and T2 is below this. Okay, and I mean by induction, of course, I can, I mean this is saying that the value applied to a convex combination of 2 points is less than the corresponding convex combination of h of those points. And of course this I can have for more points. So I mean by induction I can, from this here, I can also get that h of an arbitrary convex combination of an arbitrary number of points plus alpha m Tm is less than the corresponding convex combination of the values of h of T1 up to h of Tm, where the alphas are positive numbers which sum up to 1. So here the alpha I bigger than 0, and the sum of the alpha I is equal to 1. Okay, and then essentially, I mean, Jensen is a continuous version of this. I mean, if you let sums go over to integrals, then you get Jensen. Okay, good. But I mean, proving it in this way is not a good idea, so there's a much more nicer, direct proof of Jensen. And for this, maybe it's also important to notice that I mean, we can also, instead of saying the curve is below such lines, we can also go the other direction, namely we can say that the curve is above a line from below which supports the curve. And I mean, this of course is the tangent. So I mean, convexity also means that at any point, at least if I have a tangent, if my function is differentiable, then it's above. The convex curve is above the tangent at any point. That's another more or less characterization of this. Maybe I write this down. And this is really something which you are using for proving Jensen. Of course, not every convex function is differentiable, so you might have points where you don't have a tangent, but then you find more. You find more curves which have this property that they touch the curve at this point, but the curve is above this. And I mean, that's what makes convex functions so useful. I mean, about convex functions you can say a lot. I mean, convex functions are not linear, but they are maybe the best thing after linear, because you can, in a sense, can compare it to linear functions, because they have a very specific relation to linear functions. So I mean, if you have a convex function, then you have a lot of theory which is around them. And Jensen is only one of them. Good. Okay, so maybe this is maybe the definition, but maybe what is maybe more important, at least in our context, is that we can compare it with the tangent, or more general support lines. So first at points where a convex function is differentiable, so h lies above the tangent. So if I have a convex curve, I mean at any point, I mean whenever at any point I can draw a tangent, and I mean this is where I'm touching the curve. That's a linear approximation at this curve, and the convex function is above this. Okay, but this is also true for other points where it's not differentiable, but also at other points there are such, let's say, support lines or kind of subdifferentials, but then they are not unique. And I mean, maybe a canonical example of a non-differential convex function is the absolute value, which is not differentiable here. And at this point, of course, there is no tangent in a usual way, but essentially they are kind of subdifferentials. I mean, there are lines which touch the curve here and are below this. I mean, for example, of course, the x-axis itself, but there are many more. I mean, for example, also just lines like this or lines like this. So in principle, I mean, you have here a derivative on this side, which is -1, and you have a derivative on this side, which is +1, and you essentially you can take any curve which has any straight lines which have derivative between plus and -1, which have this property. So okay, so at the points where it's differentiable, there's only one, then it has to be the derivative, but at other points there are actually more, and there are always such lines. Good. Okay, and this is the property which we use for giving a proof of Jensen. Okay, so let me now prove Jensen. I mean, it's important, and it has a very nice proof, so it cannot hurt to do it again, even if you probably have seen it. Okay, so let me erase this. We will come back to this next time. I think I have to write it down next time anyhow again. Okay, so let me give the proof of Jensen's inequality. Yeah, so essentially I'm interested, the main quantity is the expected value of my function f of x. So let me give a name to it. Let me call it m. So this is the expectation of f of x. Okay, and now I choose exactly a support line at this point. I know at any point, I mean any argument, I can find a support line of my convex curve, which means a straight line which touches the convex curve at this point, but lies otherwise totally below it. So I choose a support line at this point, m. So I mean, as before, I mean I have my convex curve, and now I take as an argument, I take m. So m is just the expected value of my function, and at this point I take a support line. So I take, I mean, if it's differentiable, it will be the tangent at this point. Otherwise, it will be just any of the ones which I always have. So I choose a support line at m, and this means, so I have here a linear function. So this means I have so we have a linear function is given by a constant and by a coefficient of the linear term. So I mean I have at plus b. That's the equation for the support line. So there exist a and b, which I don't care to calculate. I know they exist, such that this linear function is always less than my convex function everywhere for all t. But on the other hand, it touches my convex curve, so at the point m, it is equal. So if I plug in here t equal to m, then I have equality. So h of m is equal am plus b. Okay, so that's just, I can choose such a straight line here, a linear function. So I have a and b, such that convex function is always bigger than this, and at the point m, I'm touching it. Okay, and now I just do the estimate with this information, and then I'm done. So this is, so if, I mean, Jensen, if you don't know how to do it, it looks not so clear how to prove it, but with this idea, it's actually a triviality. Okay, so, but let us see. So then, we have, so what I want is, I mean, I want the expectation of my convex function applied to f of x. Yeah, so, and maybe let me write it down explicitly. So this is, I'm integrating h of f of x with my density psi of x dx. That's the quantity which I want. But now I can estimate my convex function at any point with respect to this linear function. So I estimate this h f of x by, I mean, it's always bigger for any x. So for any f of x, it's bigger than a times the argument. So this is here f of x plus this constant b. Yeah, okay, and then of course I can split this up into two terms. So the first term is a times f of x. I'm integrating here. A is a constant, so this comes out. So I have here a, and I'm left with the integral over f of x, psi of x dx. And the second term is I'm just integrating over b with respect to my density. So I have, and b is again just a constant, so I can take this out of the integral, and I'm just integrating psi of x dx. Psi of x is a probability density, so just integrating over this, of course, is equal to 1. I mean, I'm just integrating the constant function 1. This gives me 1. And integrating the function f of x with respect to the density, of course, is nothing else than taking the expected value. So this is the expected value of f of x. But that was exactly what I called m. So this here, I mean, m was this one, and I mean, that was the point at which I took my supporting line. But then you see what I have here is a times m plus b. Maybe let me continue here. So this is a. This integral here is the expected value, which is m. So I have am plus this integral here was just 1, so I just have b. But now this is now my supporting line at the point m, and at this point it touches the convex curve. So we have that this at this m I get exactly h of m. Yeah, but m was my expected value, so this is just h of the expected value of f of x. As you see, we are done. I have estimated the expectation of the convex function is bigger than the convex function of the expected value. That's what Jensen is telling me. Okay, so I think this is hopefully clear, but you see, this is it's total triviality. You just must know what you have to do. Because, I mean, of course, you could also try to say, okay, discrete version is more or less a definition of convexity, and then you could try to approximate things, and then you should also get it somehow. But this is much more tedious. Here you don't have to do any approximation. It's just the very basic properties of the integral. But it shows the power of having the right idea. Good. Okay, so maybe now let me make, let me now make the remark where we really go into the bone, flesh of the whole thing. Namely, now we do another trick. Now there's really a trick for proving our concentration inequality, which also might look very strange. But maybe let me now tell you what the trick will are. Next time we will then really work it out, what it tells us. So we have a few more minutes, so maybe let me just say how we continue now. Let me first use this Jensen inequality for giving an estimate of the exponential function in which we are interested. And then I will do something a bit strange, but in the end, very elegant. Yeah, I mean, I can now use Jensen in the case in which we are interested, and there in particular we have chosen a situation such that the expected value of our variable f of x is equal to 0. And of course, so if we apply it to this, so if the expectation of f of x is equal to 0, then in particular Jensen tells us if I take now the expected value of the exponential function, take here minus lambda of f of x for lambda positive, let's say, and Jensen tells me that I can estimate this. This is bigger, so this is the expected value of this exponential function. The exponential function is convex, so we can use Jensen's. This is bigger than the exponential function. This is minus lambda, and then the argument, and then the argument is now the expected value. This is the expected value of f of x. Okay, but if I looking on situation where the expected value is equal to 0, this here is just e to the 0. This is 0, this is 0, so it's e to the 0, which is 1. So you see, in the situation in which we are, the expected value of the exponential function is always bigger than 1. Okay, and this allows me to estimate the thing in which we are really interested. So I mean, what we really want is the exponential function of lambda of f of x for positive lambda. I mean, that was what we got in when we applied Markov. Then we had the expected value of this divided by e to the lambda alpha. So what we need is an estimate for this thing. Okay, and now I say, okay, now I say I write this as the expected value of lambda f of x. Okay, and then I put here, just I'm multiplying it with an artificial 1, and this 1 is the one which I can estimate less than the quantity of this type. Okay, but now I introduce here a different random variable. So this one here, so I'm saying I have this here, but then this here I'm writing as the exponential of e to the, and now I put here minus lambda f of y. And y is a copy of x. So I introduce, I mean, I have my random vector x, but I introduce a copy of it. And I mean, just if it has a Gaussian distribution, then it's this estimate which I have used for this. And here I have a product of two expectations. And if I now say, okay, I take a copy which is independent from the x, then I have here independent things, and then the product of the expectation is the same as the expectation of the product. So this here is the same as the expectation of the product of x of lambda f of x times x of minus lambda f of y. If I assume that y is really independent of x, it should have the same distribution, but it should be independent. And then, of course, what I have here is the exponential of lambda, and then I have here f of x minus f of y. Just using the fact that the product of exponential functions is the exponential of the sum. So I have this here minus this here. Lambda I can take out. I mean, I put the same lambda for both of them, but I have put a minus here. So you see, I mean, I have done this estimate with a minus here. Of course, it would be true with a plus, but I really put a minus there. And now you see I have f of x minus f of y. This looks like something like a Lipschitz condition. I mean, this is something where I know something about my function. That's the point. I mean, I have to use something about my function, but it's a kind of Lipschitz condition, or maybe we have said we restrict to differentiable ones, so it's something about the derivative. But for this, I have to have things like this where I compare different x and y arguments. Okay. But still, I mean, this looks very strange. I mean, I want something about 1x, and now I introduce an additional copy which is independent, and it seems I'm looking on the same kind of quantity. So why is this better? And this is better, and that is now really the idea that actually, I mean, that this f of x minus f of y, I can write this as an integral over the derivatives of this function. So if I'm connecting x with y, and I can do this by taking a linear combination of them. So let me write it down here. So this is this here integrating over d with respect to d theta of f. And now here as an argument, I take something, I take a path in theta which goes from y to x. from x to y. So I take here cosine theta of y plus sine of theta of x, and I'm integrating over d theta. And you see, I mean, I'm taking here the integral over the derivative, so the Stammfunktion of this guy here is just this function. So this integral of this derivative is just this function evaluated at this point minus this function evaluated at this point. But this function at the point pi over 2, the cosine of pi over 2 is 0, the sine is 1. So at pi over 2, the argument here is x, so I have f of x. And then I have to subtract the function f at the value theta is equal to 0, but cosine of 0 is 1, sine of 0 is 0, so there this argument is y. So you see, I mean, this is just a very complicated way of writing this difference. Yeah, d theta, I'm integrating here over theta, exactly. Okay, yeah. And so maybe let me call this here x of theta. So this is it's a curve of vectors which are going from y to x. Okay, and now I have here, so why is this good? This side here, why is this good? This is good because this derivative of this, of course, is given by the chain rule by the derivative of this guy times the derivative of the inner guy. So it's the gradient of f of x theta multiplied with the derivative of this guy here. Okay, and now the gradient of f, that's where we have some control. That's a Lipschitz condition. We know that the gradient of this guy we can control always by L, independent of what we have here. That's good. I mean, somewhere we have to bring in our information about the Lipschitz character of our function, and for this we need somehow the derivative. So we have to write things in terms of the derivative. We cannot really work with it directly, or maybe at least for the Lipschitz condition we also need to have a difference of two arguments. But really to work this out, it's very nice to go to the derivative. Then we get this term, which we can control by our Lipschitz condition, and we get another term. We get this derivative of this guy and this guy. That's the nice feature of Gaussian variables, that if I have two independent Gaussian variables and I take combinations like this, I will get again a Gaussian variable. And even more, I get here one, and this, the derivative, is of a similar nature, but actually perpendicular to this. So this means that what I get here, this and this, is again a pair of independent Gaussian guys. So I have very good control over those things, and this is enough control to really give estimates for this in the form which I want. So I mean what, and I will recall this next time. So talk a little bit about this. The point here that doing this is really good. I mean, this is good, but I also need to know enough about this. And the point is that if I have the pair x theta, comma x prime of theta, that this is for each theta a pair of independent standard Gaussian random vectors. I mean, if theta is equal to 0, then I just getting, for this I get y, and this actually will be x. And if theta is equal to pi over 2, it will be the other way around. And in between, I have mixtures between x and y. But essentially, I have x plus y and x minus y. So those are statements about Gauss. If I have x and y, they are Gauss and they are independent, then x plus y and x minus y are also Gauss, but furthermore, x plus y and x minus y are also still independent. So I can rotate two independent vectors in such a way that I still get two independent vectors. That's a very specific property of Gauss. That's the reason why this argument here only works for Gauss distributions. Okay, but next time I will talk about this. Just, I mean, it's again, it's just simple to see, but it's a very powerful property which I should make explicit, and then we can see how we really can use this concretely to estimate e to the dis by something in this terms which we can control and which gives us at the end really the concentration inequality which we want. Okay, so the main thing will still happen next time, but we are already quite close. Good. Okay, so thanks.